Hello students, welcome back. Let's resume section 3. We went through one example of linear regression, but there are more. Let's see. Yes, we are done with this one. Let's go with this. Here's a score table of a certain class, and alright, we have something like this. I think this may be a real data that I had years ago. And even though I have all these data, I don't need any of these because here we have some reversion. Of course, the mean and standard deviation and all these kind of things we can calculate with MS Excel given time, but who has time? So let's consider only this part. And also, we want exam 1 and exam 2, so we don't need any of these either. So that's all I need. Okay, alright. By the way, here's a scatter plot. Okay, we have some linear correlation. Yeah. Positive linear correlation, alright. The correlation coefficient is 0.815 something, okay. And use a method of linear regression to find the best point estimate of the final exam score for a student who scored 93 in the midterm exam. Okay, alright, that's not too bad. Y hat is R Sy over Sx. That's the slope. And x minus x bar. Oops. Plus y bar. Okay, all right. Let me expand the font a little bit more. And what is R? That's it, isn't it? 0.815 something. Okay, what is Sy? Standard deviation of y. We only look for exam 2. One we know exam 1. So this is x, and that's y. So standard deviation of y is this one. And the standard deviation of x is right here, this one. I don't need all this bold. No bold, no bold. All right. Now what is x bar? Exam 1 is something we know, so this is 69.15 and y bar is 69.95. That's 93. So doing all these computations here, what do you have? Punch in the calculator. I'm getting, missing a parenthesis. 90.044 something, all right. I'll simply say 90, approximately speaking. Something is not right. Oh yes, there's a typo, 65.95. I just mistyped this one. Okay. 86.04. So it's about 86. Okay, all right. Yeah, that makes more sense because now in part B I'm starting from 86. Same 86. Does that mean I'm going to have to come back to 93? Well, of course, that's not the case. I'm going to use the same formula, of course. But it's going to be all different numbers because you see, up to this is correct formula, regression formula. When I know x value, I'm going to find out y value. But then again, this time is different. X value is the known value, and that is final exam. So exam 2 is x value, exam 1 is y value. It's different now. So copy and paste all those. And x value is now 86. X bar is 65.95. And y bar is 69.15. Now, correlation, and this is 0.81 something, that one. That doesn't change. Now, SY is here. And then SX is this one. So compared with previous computation here, this, that, they were reversed, and this one, that one, those are reversed, and that one adjusted accordingly from the problem. Instead of 93, I have 86. Otherwise, I'm using the same formula, it's the same computation method. So let's go ahead and finish this computation. You can use handheld calculator if you want to, but I have much faster tool. So I get here 84.98 something, so approximately speaking 85. Let me check the answer. Yeah, 85 is correct. So whenever you use regression line formula, either the slope point equation form or slope intercept equation form, they're both equivalent to whatever you want to. No matter what method you want, make sure x is known value and y is something you want to find out. You can, of course, adjust the formula itself, but if you want to keep the same formula, then you have to change x and y accordingly. Another comment here. We started from 93, and regression prediction, we get 86. And then we do regression prediction from 86, we came back to 85. What's happening? 93 is regressing to 85, and this kind of thing is called the regression effect. The regression toward the mean. I started from 93, quite a bit above the mean, but each time I do the regression, I get closer and closer to mean. So here, I'm looking for midterm exam again, so getting closer to 69.15. So if I start from 85 and do this again, regression, then I'm going to get even closer to 69.15. And so on and so forth. And this thing is called the regression effect. Regression toward the mean if I start from exceptionally high score. By the way, if I start from exceptionally lower score, then each time I do this regression analysis, I'll get bigger and bigger and bigger score toward the mean. So many people people may have called it progression toward mean, but traditionally that's not the case. Actually, let me see. Who is the person who discovered this to begin with? Excuse me. Yeah, Francis Galton. That was the name of the mathematician. And that was, when was it? Oh, I don't remember. Anyway, when Francis Galton published all these kind of results, he used exceptionally higher number and then did all these and then showed that we have regression toward the mean. If he started exceptionally lower number and proved that numbers are getting higher and higher and higher toward the mean, maybe he would have named this as progression toward the mean, and maybe we are calling all this as progression analysis. But then again, history says the other way around. Galton simply chose bigger number regressing toward the mean and named this as regression analysis, and people are simply following all those. All right, there goes an example. And here's another example. This time we have Dow Jones Industrial Average, and then S&P 500 index and NASDAQ Composite Index, and we have all these numbers. And then here's a summary version. Yeah, we don't need all these numbers. If you calculate the mean and standard deviations and correlation, we're going to get these. And depending upon where we start and what we predict, you have to select your X and Y accordingly. For example, use A. Use linear regression to find the best point estimate of S&P 500 when Dow is known. So this is X, and that's Y, according to part A. And then we are going to use this correlation. It doesn't apply NASDAQ. Now, if you go to B, use the linear regression to estimate NASDAQ when S&P 500 is known. So S&P 500, this is known, so that's X, and this is Y. And we have to use this correlation, and that doesn't include Dow. And the third, when NASDAQ is known and the Dow is unknown, so this is X, and now that's Y. You'll have to make appropriate decision about which character is which, and if you have more than one columns, then that becomes particularly more important. This problem is left to the students, and the answer key is present for part A and part B. And part C, I think I didn't bother. Oh, I did. I did? Oh no, I didn't. Yeah, here I gave you all those solutions, but part C, I didn't bother. I left as question marks. Okay, the rest is left to the students. Now let me give you one more little comment about regression lines. Depending upon textbook authors, sometimes they introduce two different regression lines instead of switching X and Y. See, here's an example. And then you can do either this regression analysis blue or that regression analysis red, depending upon which way you go. What we used to do, or what I like to do, is just stick to the same formula, the top one, blue one, and that's when you know X and you're going to find out Y. And then when you have to go the other way around, just switch X and Y is the way to go. But sometimes Some people just want to keep the same x and y and change the formula. In that case, what happens? Well, here is a visualization. We end up with two regression lines, blue and red, and then regression prediction works kind of like this. Blue line minimizes the regression error, prediction error, which is vertical distance because we are predicting y. So this is observed y value, this is predicted y value. So we are getting these vertical distances. But for the other, we are minimizing these horizontal distances, but because given y, I'm predicting x, and this is observed x. So horizontal distance is the regression error. So we are doing, instead of changing x and y and then using the same formula, we just keep x and y and change the geometry. You can do it like that too. Some textbook authors do it this way. I don't. But one good way is to one advantage of this viewpoint is to get the regression effect. Start from here and then get regression prediction, get there. Okay, same point from y coordinate, and then use red line, regression line, to get back. And let's see, from the starting point, which is the starting point of this blue, this here, a little bit bigger than 60, I regressed a little bit toward the mean. So we are looking at regression effect a little bit toward the mean, and if I do it again, and I'm going to get a little bit closer to mean, and closer, I'm going to get a convergence there. Of course, if I start from lower than the mean, I'm going to get bigger toward the mean. Either way, it's called the regression effect. All right, the final topic here. Yeah, let me de-emphasize it in gray. Some textbooks follow this. I don't. You don't have to either. Okay, so much for section 3, and let's meet again in section 4 in a separate video. Thank you.